The capital of France is Paris. That prediction doesn't seem very impressive. Your phone could probably do it. But now ask the same machine to explain a black hole, translate a poem, find a bug in some code, write an email that sounds polite but not desperate, or solve a puzzle it has never seen before. Somehow, the machine does all of those things using the same basic move. It predicts what comes next. That sounds absurd. It also hides the most important part of the story. Later, I'll show you an experiment where a language model was trained on nothing but moves from a board game. Nobody gave it the board. Nobody explained the rules. Yet, something resembling a board appeared inside the model anyway. That experiment is the clue to how prediction can grow into behavior that looks like intelligence. First, we need to fix one misleading phrase. Large language models usually don't predict the next word. They predict the next token. A token might be a whole word. It might be part of a word, a punctuation mark, or even a small piece of code. The exact pieces depend on the tokenizer. During generation, the model chooses one token, adds it to the text, then predicts again. One piece, then another, then another. There isn't a completed paragraph hidden backstage, waiting to be revealed. The response grows as the model produces it. That explains how text comes out. It still doesn't explain how the model learned enough to write code or answer questions. The answer begins with a strange advantage. Text can label itself. Take this sentence. The robot picked up the red cube. During training, the model sees the and tries to predict robot. Then it sees the robot and tries to predict picked. The robot picked leads to up. The robot picked up the leads to red. And the robot picked up the red leads to cube. One sentence becomes several tiny exams. The correct answer is already sitting in the text, so no person has to label the sentence by hand. When the model gives too little probability to the token that really came next, training sends an error signal backward through the network. Its weights move a tiny amount. Then it tries again on another piece of text. Repeat that across an enormous training collection, and the model takes this exam over and over at almost every position. The exam never changes. Predict the next token. But the questions get much harder. Peanut butter and can be solved with a common phrase. The cats are sleeping requires basic grammar. She deposited cash at the depends on meaning. The trophy didn't fit in the suitcase because it was too requires the model to work out what it probably refers to before choosing large or a similar continuation. And this pattern asks the model to infer a task from the prompt itself. English, cat, French, chat, English, house, French, maison, English, dog, French. The useful continuation is chien. Nobody changed the model's weights between those examples and the answer. The examples in the prompt temporarily showed it what kind of continuation was wanted. Calling an LLM autocomplete describes the format of its output. It does not describe the difficulty of producing a good continuation. A chess engine also returns one move. That doesn't mean choosing the move was simple. In the same way, an LLM returns one token, but the probability of that token can depend on grammar, facts, earlier instructions, the structure of a program, and relationships spread across the context. If two situations need different next tokens, the model needs some internal way to tell those situations apart. A bank beside a river and a bank that holds money may begin with the same token. But once the model processes the surrounding sentence, their internal representations can move in different directions. The model was never handed a neat list called all meanings of bank. Training pressures it to discover distinctions that make its predictions less wrong. To see where all that computation happens, follow one prediction through the machine. Text enters the tokenizer gate and gets cut into tokens. Each token receives a numerical ID. Those IDs are turned into learned vectors called embeddings. Position information tells the model where each token sits. Without order, dog bites man and man bites dog would contain the same pieces. Then the tokens enter the transformer. Attention lets each position gather information from other relevant positions. The representations pass through many layers, and each layer changes what the model has inferred from the context. At the far end, the model produces a score for every token in its vocabulary. Those scores become a probability distribution. A decoding rule selects one token. Sometimes it takes the highest probability option. Sometimes it samples from a group of plausible options. The selected token joins the sentence and loops back through the process. That loop can build an email, a story, or a program. But the loop alone still isn't the source of the capability. The capability sits in the computation that creates the probability distribution, and in the patterns, training has pressed into the weights. This also explains why scale matters, though bigger is only part of the answer. A model needs enough capacity to represent useful patterns. It needs enough varied training data to encounter those patterns. And it needs enough compute and a good enough training process to adjust the weights. Researchers have found smooth relationships between language model training loss, model size, data, and compute. But parameter count by itself is a poor scoreboard. In the chinchilla experiments, a 70 billion parameter model trained on far more data outperformed several much larger models under a similar compute budget. A giant model that has not learned enough can lose to a smaller model that trained on a better balance of data and compute. This is where the board game experiment becomes useful. Researchers trained a GPT-like model on sequences of legal Othello moves. The model's job was simply to predict which move could come next. It was not given a visible board state. At first glance, it could have been memorizing move patterns. So the researchers looked inside. They found a nonlinear internal representation of the board. More importantly, they could intervene on that representation. When they changed the model's internal version of the board, its predictions changed in corresponding ways. Prediction had rewarded the model for tracking part of the process that generated the sequence. Othello does not prove that every language model contains a perfect simulation of reality. It is a small, clean world. Real life is messy. What it does show is that when a sequence comes from an underlying process, predicting that sequence can reward a model for representing the process internally. Human text comes from many underlying processes. People describe places, argue about ideas, write programs, explain causes, solve equations, and imitate one another's mistakes. To predict all of that well, a model can benefit from internal representations of syntax, topics, entities, relationships, tasks, and fragments of how the world works. That is how a simple training objective can produce broad abilities without engineers programming each ability separately. But there is a trap here. The model is trained to predict text, not to consult a truth machine. If the training data contains a common misconception, repeating that misconception may be a good prediction. A low temperature can make the output more consistent, but consistency is not truth. The model can also generalize and memorize at the same time. Researchers have extracted verbatim training passages from language models, including rare sequences. That does not mean every answer is copied from one hidden web page. It means the weights can contain broad, reusable patterns and memories of specific text. And when a model prints a beautiful chain of reasoning, those words are not guaranteed to be an honest window into its internal computation. The explanation may help it reach an answer. It may also rationalize an answer after the fact. So, prediction can create useful internal machinery. It does not guarantee truth, grounding, or human understanding. There is one final piece that explains why ChatGPT behaves more like an assistant than a raw text completion machine. Pre-training teaches a base model to continue text. If you write, "What is photosynthesis?" a base model might answer. It might also continue with another question, imitate a quiz sheet, or invent the next lines of a forum conversation. From its point of view, those are all possible continuations. Post-training changes the behavior. Human demonstrations and preference feedback teach the model that, inside a chat, a direct and helpful answer is usually preferred. In the Instruct GPT research, a 1.3 billion parameter post-trained model was preferred by human evaluators over the 175 billion parameter base GPT-3 on the study's prompt distribution. That is a 100-fold difference in parameter count. The smaller model had not magically acquired more raw knowledge. It had been trained to use what it knew in a way people found more helpful. Now, return to the sentence where we started. The capital of France is... The final output is one token, Paris. Behind that token is a much larger process. The text was cut into pieces. Those pieces became vectors. Transformer layers combined information from the context. Training had shaped the weights across countless prediction errors. The output layer scored every possible next token. Then, the loop began again. Predicting the next token did not hand the model a list of intelligent behaviors. It gave the model one relentless test. To keep getting better at that test across the full mess of human text, the model learned machinery that can support many different tasks. But that answer leaves one problem. Before a language model can predict a token, it has to decide what the tokens are. Unbelievable could be one piece, or several pieces, or a sequence of bytes. Each choice changes how much text fits into the model and how efficiently it can learn. In the next episode, we open that machine and see what an LLM actually sees when it reads a sentence.